Hey students, welcome. Have you ever thought about why ice feels hard while water is liquid and air seems to be all around us, invisible? That's because matter, which makes up everything around us, comes in three main forms: solid, liquid, and gas. Each of these states has its own distinct properties based on how the particles are arranged and how they move. Solids, like the ice cube in your drink, have particles tightly packed together. They hold their shape and size. Liquids, on the other hand, like water, still have particles close together, but they're free to move around, which is why liquids flow and take the shape of their container. And gases? Well, gases, like the air we breathe, have particles that are far apart and move freely in all directions. This means gases don't have a fixed shape or volume, and they expand to fill whatever space they're in. Pretty fascinating, right? The way the particles in each state behave is what gives each state its unique characteristics. Now, let's dive a bit deeper into the particle model of matter. Picture this: solids are like a tight knit group of people standing in a row, barely moving, just shaking their hands a little. Liquids are like people who can move around but are still close enough to hold hands. Gases are like a crowd of people running around in every direction with no real connection to each other. The reason solids, liquids, and gases behave so differently is because of how the particles are arranged. In solids, particles are packed tightly in a fixed pattern. In liquids, the particles are still close, but they can slide past one another, giving liquids their ability to flow. Gases, with their widely spaced particles, move around rapidly, filling up any available space. And of course, the temperature affects all this. Heating the matter increases the movement of particles, while cooling it slows them down. You can actually observe this change when you heat a balloon. As the gas inside expands, the balloon gets bigger. Ever noticed how a balloon shrinks when you press it, or how a car tire seems to get harder when you pump more air into it? This is all because of Boyle's law. Boyle's law tells us that pressure and volume are inversely related for a gas. When the volume of a gas decreases, the pressure increases, and vice versa. Imagine a balloon. As you squeeze it, the space for the gas particles to move around gets smaller, and they hit the walls of the balloon harder, increasing the pressure inside. This law is written as P1V1 equals P2V2, where P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, V2 is the final volume. The subscript 1 and to refer to the initial and final conditions, respectively. So, when you reduce the space a gas can occupy, it gets pressurized, and when you increase the space, the pressure drops. This simple law explains everything from how tires work to how vacuum pumps function. Here's a fun one: why does a balloon inflate when you heat it? Well, that's all thanks to Charles' law. According to Charles' law, the volume of a gas increases as its temperature increases as long as the pressure remains constant. Think about heating up a balloon. When the gas inside heats up, its particles move faster and spread out, making the balloon expand. The mathematical expression for this law is V1 divided by T1 equals V2 divided by T2, where V1 is the initial volume, T1 is the initial temperature, V2 is the final volume, T2 is the final temperature. The subscripts 1 and 2 refer to the initial and final conditions, respectively. Just like when you heat up air in a hot air balloon, the gas expands, making the balloon rise. So, just like you'd expect, heat causes the particles to move faster and take up more space, which is why gases expand when heated. Now that we've got a good grasp on individual gas laws, let's tie them all together with the ideal gas law. Imagine all the gas laws combined into one powerful formula: PV equals nRT. This equation helps us understand the behavior of gases by relating P for pressure, V for volume, N for the number of moles of gas, R for the ideal gas constant, and T for temperature in Kelvin. If you know three out of these four variables, you can find the fourth one. For example, if you increase the pressure and keep everything else constant, the volume of the gas will decrease, just like when you pump air into a tire. This is the perfect equation for solving real world gas problems, like determining how much gas will be produced in a chemical reaction. Let's take a closer look at why gases behave the way they do, and that's where the kinetic molecular theory comes in. Imagine billions of tiny gas particles moving around at lightning speed, constantly colliding with each other and the walls of their container. These collisions cause pressure. This theory explains the macroscopic behavior of gases by looking at them on a microscopic level. It tells us that gas particles are in constant motion and that the pressure of the gas is a result of these particles colliding with the container walls. The speed of the particles and thus their kinetic energy is directly related to the temperature of the gas. Higher temperature equals faster moving particles and hence more pressure. It's like a busy highway where the faster the cars move, the more traffic jams, collisions you'll have, except in this case, the traffic jams are the collisions creating pressure on the walls of the container. Now, how do these gas laws apply to the real world? Well, we see them in action everywhere. Take hot air balloons, for instance. The hot air inside the balloon expands as it heats up, making the balloon rise. Or think about how tire pressure changes with temperature. When it's hot outside, your tire pressure increases. Gases also play a big role in our lungs. As we breathe in, the volume of air increases in our lungs, and when we breathe out, the volume decreases. Even in industrial applications, gas laws help in the design of engines, refrigerators, and even weather prediction models. By understanding how gases behave under different conditions, we can make these technologies work more efficiently. So, to sum up, gases are fascinating. Their behavior is governed by fundamental laws like Boyle's law, Charles's law, and the ideal gas law. These laws help explain everything from tire pressure to the way hot air balloons work. By understanding how gases respond to changes in temperature, pressure, and volume, we can predict and control how they behave in all kinds of real life situations. Remember, gases are everywhere and they're constantly influencing the world around us, from the weather we experience to the technologies we use. I hope this session helped you see just how essential gas behavior is in our everyday lives. Catch you in the next class, where we'll uncover more incredible chemistry.